Hello, everyone. As you have likely heard, nuclear power is in the news, particularly what is called small modular reactors, or SMRs. Governor Healy includes new nuclear reactors as a part of an all-of-the-above approach to meeting the state's energy needs. But what is the reality behind this renewed interest? Will new nuclear reactors be safe and economical? To help with these questions, I am pleased to introduce today's speaker, Sukesh Agara, Professor of Nuclear Engineering at the University of Massachusetts Lowell. He is Director of the Integrated Nuclear Security and Safeguards Laboratory, Co-Director of the International Nuclear Institute, and served as Director of the Nuclear Engineering Program from 2017 to 2024. Professor Agara is a subject matter expert on small modular reactors. We recognize that nuclear power is controversial. Professor Agara's presentation is for the education of our members and does not represent the position of the ECA Mass chapter. You may have seen in our newsletter that we are conducting a survey to understand the views of our members on nuclear power. I will post a link to the survey in the chat. Please keep yourself on mute during the presentation. Professor Agara will pause for questions during the presentation, and after the presentation is completed, you can ask a question by either raising your virtual hand or putting your question in the chat. And with that, I'd like to introduce Professor Agara.
Well, thank you, Ernie, and ECA for inviting me to this presentation today. I wish I was doing this in person. I'm a people person, and I like to be in a setting where people can, interactively ask each other. But this allows us bigger access when we're doing it virtually. So we'll try to make the most of this time that we have together. So let me share my screen. I'm assuming you can see my screen and everything should be working as intended.
Yep.
All right. So, and I really like the topic. Deep dialogue is exactly what we need to have in order to confirm that nuclear energy is indeed a solution. So I actually spent about a good part of about 18 years in the South, a couple of years at Tennessee at Vanderbilt University, and then at University of Texas at Austin, where I got my degrees. And then I worked at Texas A&M. So I moved to New England in 2012, and all my friends in Tennessee and Texas were saying, "What are you doing? Why are you going to Massachusetts?" And I said, "Well, because I like challenges, and I also like opportunities." And I feel that the environment in the Northeast is uniquely poised for a more comprehensive energy solutions, which are unique to the region. I also think that the population up here is very, very cognizant of what they want to do with the land use. I think there is a heightened awareness of preservation of land, and I love that. I have two young boys, and we love being up here, and we love the nature. And I feel that this is the right kind of environment in which we can have a healthy, intelligent dialogue around how we solve our technology-driven energy needs and continue to do that responsibly. So I have really been able to sharpen my understanding of what what people's concerns are and what the technology solutions should present so that we can do this responsibly. I was traditionally a reactor core design. I did a lot of radiation transport work. Over the last 10 years, I do a lot of work internationally on nuclear nonproliferation and nuclear safeguards. Part of the reason is that there is a tremendous growth in nuclear power and nuclear power interest in the globe, and especially outside of the the developed world, the OECD countries. And so it's exceedingly important for the United States to be at the table and making sure that not only the basic international treaties are observed, but that the U.S. can provide even a leading role on nuclear security and safeguards. So, been very fortunate to have the opportunity to work across the globe on a variety of nuclear safeguards and non-proliferation issues. And in the last 5 to 6 years, I've been particularly using my experience over the last 30 years on understanding how total energy systems work, how the grid responds to energy demand, how do you make energy affordable, and how do you use the technological understanding to develop models that can hopefully make this renewable energy as it gets onto the grid. There needs to be a more responsive grid, and how other traditionally baseload powers can actually provide that opportunity of responsiveness. So yeah, I'm going to step back in history and understand how energy continues to be one of the things that drives the human population as we developed over the years. And our ability to harness energy in different ways continues to be a bedrock in our technological advancements. And it's actually almost exponential as you start to see how we diversify the way in which we use forms of bound energy. So obviously biomass, that's how we normally were approaching things back in the early days. And then we discovered a lot of basically fossil-based fuel sources, mainly coal, petroleum, natural gas. We had an understanding of using the natural resources like the power of the water and hydro, and also wind. You know, windmills are not an uncommon thing. But as we start to scale our utilization, we had to learn how to do that in an efficient, effective way. So this is sort of a nice little snapshot that was put together at the University of Chicago Climate and Energy Policy. And they show how electricity, as the way we used it, was basically non-existent in the 1880s into the 1900s. But as we learned, the opportunity that exists with electricity, because now you can actually generate it someplace and then move it somewhere else, and then start to find a different way of utilization. The growth in the way that we start to use electricity is expansive. And so in 1954, I mean, you see that the electricity component, so the scale basically shows you how we consume energy and at what different categories. So EIA sort of looks at 4 different major categories: residential and commerce, agriculture, industry, and transportation. And it's evidence that in the beginning, a majority of all electricity was mainly used for commercial and residential buildings. But as we start to look at where we're going, the demand for electricity continues to grow, and we're learning how to make electricity using more than different kinds of resources. And we're learning that we can essentially reduce the overall carbon footprint, or at least consolidate, and hence be more responsible in terms of how we put that carbon out into the atmosphere. And so in this graph in 2019, you can see that, you know, beyond the residential use, the electricity is now found creep into the agriculture applications, industry, and then very, very soon, I mean, even in this last 5 years, the expansion in the transportation sector is obviously very high and anticipated to be great. So if you start to sort of shrink all of that into a similar graph, but now just as the total energy consumption, this is why we are all here. We are talking about this because in spite of all of the technologies that we just talked about and centuries of experience working with other forms of natural resources, including wind and water, we still find carbon-based sources as very convenient for us. And it is, in fact, very pervasive in our daily use. So basically 81% of all energy that we use is still carbon-based. About only 20% is non-carbon-based source. And of which, if you go into electricity demand, about 25% is nuclear, Still 23% is coal, and then you have about 10% renewable. And if you really break down the renewable, you'll start to see that there's still actually a biomass component that dominates. And so I think we still haven't really sort of really separated ourselves away from fossil or carbon-based sources, which is why there is an anticipated electrical sector growth into the next decades. And we're going to probably electrify more things, including heating sources, transportation, and others. So there's going to be a growth in demand, and we need to make a choice as to how we do it responsibly and affordably while we actually clean up the source and hopefully go to net zero carbon. So if you look at the cost of energy, it's not only an affordability from the macroeconomics point of view, but it also has a significant environmental impact. And it is very evident when you look at lots of studies that show the developing countries normally, including ourselves, when we were in that rapid growth, we tend to choose economy over responsibility as much as we can. So we try to choose the cheaper form of easily available resource as we can. But it's not just about being cheap. It's also about national security. Normally, when you can use resources that are in your own boundaries, you tend to do better in terms of your overall national security plan as compared to looking for an import of resource. And it became particularly evident in Europe as some of the Russian sanctions were put in, and the Russians were the major suppliers of natural gas and petroleum to the central western parts of Europe. So again, national security becomes a critical issue, and then obviously sustainability as we look forward. So why should I care about nuclear? When you think about nuclear, and this includes a lot of us, we either think about nuclear weapons, we think about all the spent fuel storage that's sitting in various places, and this image actually is more recognizable in wide audience surveys than many of the other images, and that's the Fukushima accident that happened, now a decade ago. But again, these are lasting images that we need to understand, and we need to be able to explain and see how it works. So, when we think about nuclear, rightfully, there's all these concerns, right? Public and plant safety, nuclear waste. We don't have a solution. Nuclear energy share down. It's actually not it's about 14%. It used to be 14%, it's 9%. SMRs, small modular reactors, and advanced modular reactors, maybe they're a hype. None of them been built. Not on time, never at cost. Nuclear industry has had an issue with that. Maybe it is a thing of the past. Maybe it's a technology that is a relic and not something that is of the future. So why not, invest massively into fusion? Why not, go into renewable and storage solutions? Because those are also clean. And maybe they don't have the baggage that some of the nuclear technology has. So if you really take a first look at it, you can walk away thinking, I'm not impressed. And honestly, that's okay with me. I think we should all not be impressed till somebody proves us otherwise, right? So my hope is that I can share some of the things that are ongoing right now and the pressing issues as to why we need, and Governor Haley's approach as well, in terms of we need to look at all of the above and make some responsible decisions that will provide us a path forward. So why should we talk about it? Well, we need to talk about it because there is a demand growth. In fact, we had in this region, in the ISO New England, because of all of the very aggressive efficiency upgrades and other things that we did in this region, we were able to actually move the demand curves down. I'll show you that. But it's going to now, we kind of squeeze the apple as much as we can. There's no more cider to be had. We need to figure out where we're going to get the new bushel of apples. We definitely have a very stated decarbonization goal, and we need, I think that is none of us who are on this call would disagree with that. I think we can decarbonize, we should decarbonize as much as we can, but we have to do it in a phased approach. There's no on and off switch on this, and we need to figure out how we can do it responsibly. Whether you believe in climate change, that's a debate in itself, but we can definitely at least see extreme weather. Extreme weather has been a part of human development for centuries, but the impact of extreme weather continues to be even more significant because our populations are congregating into locations, and we are very interdependent globally. So sometimes, we may be able to be more self-sufficient and could weather an extreme weather event in the past, maybe even centuries ago, but it's becoming much, much more difficult to do, as we will see later on. And then energy affordability, energy is something that is essential for all population, and we can't just ignore it. So I wanted to kind of highlight the importance of energy demand, and there are lots of factors that influence that. Decarbonization could really put a lot of pressure on our demand for electricity, or growth in electricity demand, especially if you want to take the transportation sector. As you go into the EV deployment, you clearly going to have a demand for electrical capacity. So this is the ISO New England's 2024 capacity report that just came out, that shows where we are going to be in terms of the projected growth going into the next decade. I kind of talked about extreme weather. Extreme weather is really now you need a grid that is actually resilient. So it's not only an ability to have a reliable energy source, but we need to have a resilient energy source, right? Especially in the Northeast. I lived in Texas when there was a major hurricane that came through. It was hot and uncomfortable, but honestly, once the hurricane was gone, I could just open my windows and be out there. If we had an extreme event, weather event, and I'm going to show you one of those, in the peak winter months, it's a different situation. Can't really do it without maybe a fireplace and kind of figuring out a way to kind of make that work. And there's a anticipated and well-documented growth that comes from the electrification of transportation and also heating. So if any of you have actually taken advantage of putting a heat pump, literally what you're doing is either replacing or reducing your reliance on a fossil-based fuel, whether it's natural gas, oil, coal, wood-burning fireplaces. You're essentially putting it, a heat pump is essentially going to now run on the fan that's on electricity. And when you scale that to many, many homes and industrial or office buildings, that electric demand will creep. And then there is a reliance on AI. Whether you believe in AI or not, whether you use it or not, it is actually now pervasive across the board. Some of it is very straightforward and simple. Just your search engine in Google uses an AI algorithms that essentially makes the search more efficient. And then there's more complicated applications of AI, such as we are using machine learning and artificial intelligence to essentially look at very specific design of engineering components. So there is a lot of scale in terms of where AI would get used, but it's definitely going to get used. Anytime when you have a computer algorithm that runs, which is in layman's term AI, it requires compute power. So NVIDIA, GPUs, you may have heard, or CPUs. Essentially, you need computers that crunch this information. And so it was necessary when we were running just essentially just servers that made your search engines more efficient. And then these search engines are major energy demand centers. So as you start to add more data centers, there's going to be a greater demand for energy, and particularly electrical energy. And then reshoring, as we are looking to bring industrial production back home, we need to be able to provide a competitive energy source, not only a competitive labor. And most any manufacturing that comes back to the United States is going to use some form or some level of automation. So every robot or every robotic arm, manipulation, assembly lines are also other energy demand curves. So from that ISO England report, they basically are showing something. This could be good news for renewable energy, right? If you are a renewable energy, because it's an intermittent source and you're only using it up and down, the good news with this is we used to have a high electrical demand curve in the summer months with a low in the winter. If you look at the future, what they're looking at is a across the board almost flattening of that energy demand curve. So you're looking at about 27,000 megawatts of power across the board, summer through winter. So this could mean good things. This could mean that you would have a demand for a greater baseload power. You could also absorb better variation in your renewable energy production. And then you can also complement that by some storage capacity. But overall, basically the curve's shifting up, which means that your baseload demand is going to go up, your EV demand curve is going up, your heating demand curves going up, and you need to offset that demand with some kind of responsibility. I kind of mentioned this, and I'm not, there's a whole presentation on this by itself. So there's a lot of conversations and real money flowing into the nuclear technology development, primarily because of the generative AI data centers. So all of the big techs, so this is the easy ones to follow, right? Amazon, 1.2, it's like a $2 billion investment. Google, $1 billion investment. Microsoft invested a $1.2 billion on a power purchase agreement on the 3 Mile Island Unit 1. Meta, same thing. So every major corporation and everybody underneath them are all making significant investments in all forms of energy technology generation, but particularly of note is them going in to the nuclear energy, because they have run all of the different models, economic models, reliability models, and they keep coming back and saying that the only way they can get there is by, potentially 3 to 4 times the nuclear capacity that's currently existing. So as you start to look at the decarbonization path, and if you really look at this risk analysis that one kind of is traditionally looking at and the impact, you really have to kind of dive deep into this to look at, well, where's my impact, right? How do I make something safe and clean? So path to clean energy, you're looking at solar, wind, and nuclear, which is where you have the greatest potential for growth. Hydro, we've tapped in pretty much everything we can. We can potentially have some new technology that can give us a little more nudge to increase the capacity, but it's really there's not a whole lot of scale capacity on there. So we can all agree that this is where my best growth potential is. And if I was going to be emphasizing solar, wind, and nuclear, the conclusion is we need to quadruple all of them in order to replace all of the fossil fuel that we currently use if you want to decarbonize or get to net zero, and to offset the demand growth that is coming in of the anticipated technology development. So here's just an example of the extreme weather. So this is really from us. This is the data from the ISO New England. By the way, if you don't have this app downloaded, it is a fun app to have. It's really gives you a real-time data on how the energy is being produced on your grid and how it is being supported to your grid. And it actually gives you real-time pricing too. And it's called ISO New England. If you just search it on, I can put the link on there too. But so this is just basically a snapshot where the energy mix on December 2017 right? So the average fuel mix, right? So what am I looking at? I'm looking at what different fuels are producing my electricity that is being supplied. And so you see that there is a very, there's a very small percentage, 0.3% of the energy was coming from oil, right? And that's because I'm operating under status quo. On December 26th, from 26th to January 9th, because we had an extreme cold spell in 2017, the portion of oil is about 27%, because a lot of our reserve capacity on resiliency is essentially in oil peakers. We are transforming some of them to natural gas peakers, but essentially they're going to be your peak energy demand that is coming from a fossil-based system. So you can see, in fact, one of my students actually writing a paper to show the correlation between the temperatures of the day and the carbon dioxide emission. So clearly, all things being equal, now you've really added a significant load of demand, and that was basically offsetting oil burning peakers. And then lastly, why our governor is talking about energy affordability? Well, energy affordability, it goes beyond just the cost of energy, right? It's the cost of generating an energy and then transmitting that energy and making that energy available. And so one place where you have a high risk associated with fluctuation in price is if you look at the source from which you're taking your energy from. And in this graph, this was actually done by one of the European energy evaluation, Ariba, but it's very applicable to US. I've seen other US reports as well. Because the capital cost is relatively low on the natural gas system, the majority of the cost is your fuel price. So as soon as the fuel fluctuates, it essentially comes directly onto the ratepayer. Whereas if you look at nuclear, the biggest cost is cost associated with capex, so your capital costs. But then there's very little to no variability in price or influence of price to the ratepayer based on fuel, because it's a very small fraction of the total cost. So when you start to deploy a certain form of energy generation capacity, if it is heavily weighted in one direction, you end up having a very high capital investment cost, which is infrastructure development, or you end up with a low capex, but a high fluctuation influence on what your ratepayer is going to have to accommodate for. For some of us, or majority of us on this audience, maybe we're in a good place in our financial planning that a 20% change in an electric bill over a few months, we may be able to absorb. But there is a whole segment of population where they do not have the ability to just absorb that 20% fluctuation in cost. And so when they're doing their budgets, they don't have that kind of a buffer built into. So energy affordability becomes very critical, which means that as you stretch things, so nuclear really works well there. If you stretch the nuclear power, the investment is over long term. So you know that you're going to have to spend this much on capex for the next 10 years, 15 years. Then your fuel cost is smaller, which means that planning wise, it's actually a nice combination to have in your overall energy mix that offsets your overall cost planning. I won't spend too much time on this, but again, if you really start to break this down, so I have a PhD student actually working on this model where we really run the specific details, because what I was describing to you earlier, you can actually build out computational models that take all of these various different real-time data and then run simulations to understand what would be the impact as you vary the capacity on the grid, and also as you vary some of the factors, the variables, such as temperature, gas prices, and other things, to look at what those influences are. So when we look at energy as an essential and affordable need, the economic picture is much more complex. And we've been a beneficiary of some of the investments that maybe some of the people on this group decided to make in the 50s and 60s. We made the investments on those long-term infrastructure costs, right? So distribution line, your transmission lines, even some of that nuclear capacity that was built in. that has been giving us a very affordable energy for a very long time. As those infrastructures age, we need to replace that infrastructure. So that infrastructure is sort of a long-term commitment to something that allows us to, levelize our baseload power demand, right? And so I think it's time for us to make some very specific choices as to how we're going to get there. If we were to deploy significant renewable capacity, we need to still make infrastructure investment because we don't have all the transmission lines we need. We don't have all the distribution that we're going to need. So we need to invest there. If you're going to also balance that with some additional nuclear capacity, we need to sort of make that capital investment in those nuclear projects, which will keep us giving us clean energy for 60 years with a payback time of 15 to 16 years. So it depends on how you run that. But anyway, so there are lots of these economic factors that become very critical as we start to look at these things closely. Again, there's a lot of things. So now I'm going to pivot into how nuclear is looking, right? So I kind of painted the picture as to we're going to have an energy demand. We are going to have to make some very critical capital investments to improve our infrastructure, and we're going to need to kind of think about diversifying our energy source. So now, where is nuclear in all of this, right? So nuclear energy has been dormant in this country, right? So we hadn't built a new nuclear power plant in 28 years. And so we kind of benefited from all the build activities from the 60s, 70s, and 80s. We had more than 100 reactors deployed all over the country, and that was providing about 20% of the power. And it continued to produce 20% of the power in spite of the fact the energy demand in that 30 years went up. So how does that happen? Well, the way that happened is when we first built the reactors, we were learning how to use them efficiently, right? So there's something called the capacity factor, which means that the capacity is to produce 100%. Well, what does it really produce, right? So if you look the year back and you say how many days out of the year was it actually operational? The capacity factor of the nuclear reactors in the 60s and 70s was horrid. It was in the 50 to 60%, which means only half of the year it was actually producing electricity. The other half of the year it was actually closed, shut down for maintenance. It was, going through refueling, things like that. The industry really came together and learned how to operate and maintain reactors consistently, safely, and efficiently, right? So think about it as you're teaching your 16-year-old, I'm using that example because I have a 16-year-old, how to do all the checks in a car. He's slow, right? He's going to learn how to, I'm like, okay, well, if you had a flat, what are you going to do? I don't know. It takes him a while to kind of go out and find the jack and then put the jack in, it takes him a very long time. If you look at a Formula One racing, they can change all four tires, all the oil and everything else in a matter of minutes to seconds. That is how efficient the nuclear fleet today is. We are at about 93% capacity factor. What does that really mean? Which means that in 30 years, when we went from about 60% capacity factor to 95% capacity factor, we effectively build 30 new nuclear power plants, right? Because you had 100 reactors and you improved your efficiency by 30%, which means you literally had 30 new nuclear power plant equivalent on the grid, which is why we didn't build any new nuclear power plants for 30 years and still maintained a 20% of the total electricity demand on the grid. And this is very much something that's missed. So when you start to look at the broader impact of the economy, you start to look at some of the specific laws that have been passed that allows for the new nuclear to again be in that competitive space to provide us with the next 60 years of reliable clean energy and maintain that 20-30% of energy offset. This is what other countries have looked at. They have looked at the data, they understand the demand growth, and that's why you see so much construction going on nuclear power plants and newcomer countries coming into the mix as compared to what the OECD countries were doing. We weren't just writing nuclear off. We were improving how we used our nuclear power. We were gaining from that experience equivalent of 30% new nuclear power plants, which is why we got away with not building any new ones. But now time has come where we need to figure out how to build new ones because we've been using nuclear power and some of these reactors for 40, 50, 60 years. Some of them need to be sunsetted, and the technology has improved significantly. So we should think about how to build our new fleet. So now I want to kind of level set all of us into the thinking of what does this mean, right? So when you're thinking large scale reactors, these are essentially something that is from 300 to 1,000 megawatts. So every single reactor that was built back in the design and build in the 60s, 70s, and 80s essentially was in that 600. Initial fleet was about the 600 megawatt reactors. So our Pilgrim reactor, which is a boiling water reactor, was about 682, 86 megawatt electric. And then as we build some of the last ones like Seabrook, we are at almost about 1,400 megawatt electric. So the designs themselves improved. So on the same site, now we're producing almost 3 times more energy because we also improved our design, right? So these designs are the first designs were called the Mark 1, Mark 2. The one that we had was a Mark 2 BWR at Pilgrim site. And then the reactors that are built. So for example, the one at Seabrook is a generation 3. Generation 3 plus is the 2 reactors that are built at Vogtle in Georgia. So these 2 reactors essentially have some of the very unique attributes that essentially addresses all of the safety issues that we learned after operating and continuing to operate about 50 years of our nuclear power fleet. So some specific example is they have all the generation 3 plus reactors all have a passive safety system. What does that mean? Does that make that reactor more safe than the reactor that's in Seabrook? No. In Seabrook, I had to spend more money, several $100 million more, in order to bring those safety attributes to an existing plant. So, for example, if you had a nice antique car that you restored, now you need to put, if you wanted to put in airbags because you know that they make you safe, you need to put in seat belts, you need to do all those upgrades into an existing antique car. You can absolutely drive that car. You can put air conditioning in there if you want, if some of you are car enthusiasts. And you can actually add all of the other safety mechanisms, right? But that costs you a whole lot more, and it will never go as fast as your modern car. So at some point, you come to a position where you say, hey, you know, I'm better off not putting more and more money into this car to make it more and more safe or change its attributes or produce a little extra power, but now I'm better off just completely redesigning and rebuilding, right? So the AP1000, for instance, it's called a gigawatt reactor, right? Because it's about 1,500 megawatts electric. It uses 50% fewer valves, 83% less piping. So this is a big deal, right? So if you're running 10 different pipes to basically get the water to your bathroom, it's basically a big spaghetti of pipes you got to do, right? And then you have to evaluate safety. If you're an industrial complex, like heavily regulated like nuclear, you really have to have a bunch of engineers who are literally just inventorying everything that you got. So not only is it expensive to build, it's also very expensive to maintain. And regulations require you to kind of keep doing it. So you can imagine when you can reduce 87% of the cabling that goes into the reactor. It significantly changes how you're going to operate and run those reactors. So these are some of the things that are clearly built into the generation 3 plus reactors. This is the advanced gigawatt reacters. The new thing that is actually going on is the small modular reactors. So these reactors are 20 to 300 megawatts electric. And what makes them modular is that a big chunk of it is actually built in factory. As compared to the gigawatt reactors. So gigawatt reactors are like your custom home. Got an architect, you got a civil engineer, and you're going to pour concrete. You're going to bring those guys right on site. Everything is going to be done one step at a time. We basically built 99 out of the 107 reactors in the country that was one of a kind, right? Each one was built from scratch. Everything had to be done. We had lots of engineers on site. We had to do it. What now we've learned just from fundamental construction engineering is you could be more efficient. I mean, in fact, you might have seen bridges, you know, where you can bring sections of bridges and then you put them all together. It's faster, it's more efficient, and it's actually cheaper. So small modular reactors essentially open that avenue. Now you're able to do something where you build a pressure vessel, some of the components of the reactor in the factory, and then you're going to assemble them at site. Well, that's nice, nicer than the large gigawatt reactors. But the third category, which is the micro reactor. So now these reactors are basically sometimes even called the nuclear battery if you're like 1 megawatt. These are literally loaded onto a truck bed and they will roll in and they're just hooked up. If any of you have a Tesla electric battery, the power walls, you know what I'm talking about. They essentially on your wall. If the power goes out, it basically switches over. You don't even know. If you have one of those generators, gas, but automatic electrical switch, that's kind of like it's still installed, put on there. You got to have to make sure that the switch flipped. I have an old generator where I have to actually, plug it in, make sure it all goes, it goes. So essentially, as you start to improvise, you can start to shrink the time to construction, right? So that was one of my big concerns with nuclear power plants. So they can't build them on time. Well, if I go to small modular reactor, I have a more confidence that I can build something more quickly. It also reduces your capital costs, right? Because if I need to come up with, so per megawatt or per kilowatt hour, it may cost you a little more, but you're able to offset your capital cost investment. Right? So I can build my 300 megawatt electric, and then I can add more capacity. So I can get to a gigawatt, but I can do it in stages, right? So one of the biggest issues when you have capital intensive projects is until you live in it. So let's say this is the example of living in your home. If you're building a home, while you don't have the occupancy certificate, you're going to have to pay somebody else, rent a space, and you got to be there, right? So you're not generating you're not saving any costs. So you're just forking out money on both ends. But once you're able to occupy, your cost of rent is gone, right? And now if you're building a rental apartment in your home, now you're going to start generating revenue. So a nuclear power plant is kind of like that, right? So you're going to spend all this money to build a plant, but you're not making any money till the first electrons got in the grid. So you can get to that first electron a little bit faster. It's about 10 years for a gigawatt reactor. It's about 3 to 5 years for a SMR, and then it'll be about a year or less for microreactors. So this is a sort of a very specific solution to the known problem that we had with the construction overruns and time to build these reactors. So sort of just a viewing as to what that looks like. So EBR was the first reactor that we ever powered in Idaho National Lab. Basically gave us the first electrons to power up the bulb. The Generation 2 reactors is the Pilgrim Power Station, in Plymouth that we decommissioned. Generation 3 is Seabrook Power Station, which is not so far from here from Lowell. And then Generation 3 Plus is the Vogtle 3 and 4 that I talked about. Much more compact. You can see the size of the footprint is actually much smaller compared to even Seabrook, which was actually a pretty state-of-the-art reactor in recent times because that was one of the newest reactors built in this country. And then NuScale, which is one of the SMR designs, actually has even more attributes that further reduces some of the concerns associated with power. So one thing that you can notice is that actually the pressure vessel, the reactors themselves are below ground, and there is an additional water, it's called a water pool. And if some of you have ever come and visited us at the UMass Lowell Research Reactor, and I welcome if you want to come visit, we have what is called a pool type research reactor. So in the other reactors, the Generation 3 Plus, we essentially have different ways in which we push water if in an event of an accident. In this case, it's essentially sitting in a water pool. So when the event of an accident happens, unlike Fukushima, for instance, in this case, you have an additional barrier. And it's below ground, which means you have additional barrier again. So there's actually 5 to 6 total number of barriers between you and the environment in event of the worst scenario accident. So again, some of these things, and now we're layering more ways in which we are containing a potential worst case accident so that we have more time to respond, better ways to contain it, and we're actually eliminating or reducing or basically significantly lowering the probability of accidents itself. So again, like we'll use the cars analogy, as you have more sensors for, a potential blind spot, or you have a potential for, getting too close to somebody. Those sensors give you better ability to reduce your risks of accident, right? So it's actually improving your chances of avoiding an accident. And then you have seat belts, side airbags, and other things to further reduce the chance of fatality. So I know I kind of introduced you to a lot of things. I can pause here for a few minutes, and then we can kind of conclude with a few specific examples of where some of the advanced reactors are going. So just to kind of give you an idea, where are we right now? We have the experience of building 75 different reactors 4 decades ago. We now have more recent experience of building the 2 reactors, Vogtle 3 and 4, which were built with 7 years of delay and $17 billion cost overrun. I'm never going to hire that contractor again. Okay. Well, I wouldn't, right? But then you can say, okay, what did you do between 3 and 4? All right. Well, we reduced the cost by 40%. Well, it's 40% less, but it's still, twice as much as it used to be. I mean, what you told me it was going to be, and 7 years too long. So what are some of the factors? So the industry and, independent agencies have evaluated where some of the potential issues were. Some of them were on the regulatory side. Some of them were on the enforcement side. Some of them were with the inexperience of building these kinds of massive projects in the country. Some of them were associated with supply chain. So we collated all of that, and we actually, in a systematic fashion, evaluated how you can actually reduce the risks of such overruns and such. And so there's a direct correlation. As you stretch the time out, it's obviously going to cost you more because everything goes on. So if anybody's ever done a home project, you know exactly what I'm talking about. But when you do the same home project again, you're definitely going to know. You're going to, notify your electrician before you do your rough construction framing. You reach out to the electrical inspector and get on there, so you can shrink your time from when you've never done it the first time to the second time. And we had not done anything. There was a whole generational gap, right? 30 years of not building a nuclear power plant. We went out and built, several of these in China, but that was, we were looking, using the local Chinese labor force. So we didn't have that experience. Now we do. And then if you start to think about the restarting of reactors, there's a significant amount of activity going on in there. I'll have a couple of slides on that to show. So there's been some very concrete factors that gives me confidence that if we were to pursue some new nuclear power plant projects, these experiences are going to shape our ability to do this more efficiently, at better cost, better time. So let me pause here and let's, I think there are a few questions that were on the thing. So I see the issue with the 20 billion, 7 years behind schedule. Westinghouse went bankrupt. Yep. And then the NuScale SMR failed. Investor dropped the project. Yep. So both of those, I think I kind of addressed the Vogtle issue. There were some very specific lessons learned. But what could be reassuring is the fact that from 3 to 4, there was a noticeable change. And then post 4, there's a whole list of things that people have evaluated as to what were the cost and time delays, and how do we actually fix them. And there was an actual Southern Company project planned for the other 2 units in South Carolina by Georgia Power, and now they're actually back. VC Sumner, they're back in the conversation, and they're likely going to move forward. NuScale SMR, another one of those things where the demonstration project, this was with the Utah, Idaho, that was their first of the kind being built and planned. The Utah municipality had the clause in their ability to, cancel contract. Essentially, they pulled the trigger on that. rightfully, because they were able to, when they were looking at certain, they put in very strict milestones, right? So this is also lessons learned. You can put in more benchmarks. I mean, if you've done, again, construction projects with contractors, you know what to ask them the next time, right? Hey, I'm not going to give you 50% of cost up front and then just hope that you're going to do everything right. So there's been, the industry has learned, right? The utilities have learned, the investors have learned, and the actual construction companies have, the EPC contractors have learned. So everybody's kind of learned from this experience, because we really honestly did not have the experience because of the not having done anything in this country for 30 years. SMRs are basically on the drawing boards. There's no working SMR in the US. It will take at least 10 years to put one online. Most of what you said about SMR is merely theory, not one is working. I wouldn't argue with you that it is, none is currently connected to the grid. But I think it is not true to say that it's theory, because there are actual pressure vessels, 7 of them built, and there's actually all of the components of the NuScale reactors have been demonstrated to work. All of them put together in a single site and connected to the grid has not been done, agreed. But also, in this country, the Nuclear Regulatory Commission had not licensed a new reactor in 3 decades. NuScale literally had to, I have a bunch of friends who are all nuclear engineers who were working for the Nuclear Regulatory Commission, literally learning how to do this. I am sure some of you have taught your kids and your grandkids. They are smart, they're efficient, and they're eager to want to do something. But when you teach them to do something once, it is unlikely that they will become the best hunters and fishermen. But if you do it consistently and if you commit to it, they will get good at it. Engineering is no different. You can design all you want, and that's what I did for 20 years, but we never built things. Now we've actually full-scaled components have been built and demonstrated. We also have more than 10 years of the Nuclear Regulatory Commission where we replaced and enhanced the workforce, which means that there are actually people with now 20 years of having worked at the Nuclear Regulatory Commission, not looking at retirement, but looking at 20 more years of their career. And they had the experience of working with NuScale. And I'm going to show you a few more of what's going on right now. So there is a lot of actual activity going on. This is like every weekend, now you're back at the lake fishing with your grandkid. You are teaching him, you are teaching her, you are experiencing that together, and there is no substitute for that. And then now, we build more than 40 plus reactors in other countries, which we are sort of starting to tap into that experience. So there's a lot of things that have changed that was not the case 10 years ago. So I think it is right that we can be skeptical, but we also need to accept that some of these things have done. Just because I fell off my bicycle when I was doing it for the first time as 3 years old does not mean that I would not know how to ride a bicycle. If we took that attitude, then there's no future, right? Basically, you say, well, you couldn't do it the first time, you're never going to. So I would argue that there are some significant tangible changes that are out there. Shows nuclear, you have up-to-date energy use without Pilgrim. We're going to do this. What are we going to do with the nuclear waste? Yep. So I don't have I do have some other graphs I could share. Basically, when Pilgrim went off, the overall percentage dropped by 3%, I think, in terms of where we were, because mind you, Pilgrim was the smallest of the 3 plants that we had on the grid. And if you saw the demand curve going down, so that was where when we were going off in 2019 and we were ramping up stuff. But what's a better thing to look at is the percentage of the total energy that we're producing and the total energy that we're consuming as an integral, and what percentage of that is fossil fuel, right? I mean, that's really, when you're looking at 27,000 megawatts of capacity that we need on our grid in ISO New England, taking off a 656 megawatt. But if you actually read the actual detailed reports, it still had a significant impact, because what happens is when you take a baseload reliable, cheapest source of power off the grid, you start to now offset that with other forms of energy that you have to make choices
It's
on.
5 o'clock.
So honestly, Pilgrim went offline in 2017, 2019 decommissioning plan. There was also the pandemic that had a noticeable disturbance in the way that the energy consumption curves look like. But I think if you start to look at 2023 and forward, I think we can start to get more confidence on the data there. Nuclear waste. So I get Arnie, I think do you want me to stop at 5 o'clock? What do you want me to do? I know we're kind of at time. I have a couple more slides, but
Actually, we were going to go to 5:30. Our typical
Oh, okay.
dialogue is 90 minutes, so we still have 30 minutes.
Okay.
If you have 30 minutes.
Yeah, no, I don't mind. And I think, we're doing the Q&A, so along the way here. So actually, nuclear waste is a good question, and I would love to show you why some of these advanced reactors are actually sort of important and integral to the overall planning, because many of these reactors are now, this is the danger. I'm still figuring out how to intelligently talk to my intelligent audience without going into the deep dive. And I'm not saying that you're not able to, but I mean, how to make it accessible. So every reactor that's been built currently, we have two specific things that you need to keep in mind. One, we have what is called an open fuel cycle. So we basically only do a once use, once through. We don't close the fuel cycle. So in the old days, it's like, every aluminum can that you use, you threw it out everything went to the landfill, right? So that's your one issue. We normally don't look at aluminum anymore as a waste. We actually look at it as a resource. And nuclear spent fuel is actually a resource because there's a sufficient amount. In fact, there's only about 5% of usable fuel that actually gets used. The other 95% is a combination of different things that we would actually want to reuse. There's about 3% of stuff that we need to worry about, but a lot of that is short-lived, and that's your radiotoxicity. It drops significantly in the first 7 years. So a lot of the spent fuel that we have in this country now is actually an invaluable resource. Now, we did not build the reactors with the intention of taking that spent fuel and doing something with it. So there's going to be some, we're going to have to decide, is that's what we're going to do. There are a few companies that are literally designing the reactors to specifically take that spent fuel and make that as their fuel. So essentially, they're going to use that spent fuel and start producing energy from it. Not theoretical. It's actually doable. At scale, yes, we have to demonstrate that you can take that from a lab to a demonstration reactor to scale. But that is engineering 101 for everything. There is no overnight solution. I mean, we have electrical batteries for years and years and years. But in order to make electrical cars reliable, engineering solutions, cars that run on the car that you're willing to buy and drive, that is real engineering. And I think it is very difficult for people to understand and appreciate what it takes to go from theoretical reactors to lab demonstrations to actually building them and then running them. So yes, but we have to make that decision that we want to do it, right? You can't just say, well, it's theoretical, we're not going to get there. So there is a actual solution. So French and Japanese actually do close their fuel cycle, which means that they actually take all of that and reuse. So for every fuel load, every 18 months, the fuel that gets used in a French reactor, the spent nuclear waste, if you want to call it, essentially is an equivalent of a Coke can. After they reprocess everything, reintegrate. That's still an imperfect solution because we are still trying to use it in what is called light water reactors. When you go to fast spectrum, and this is where you can get really fun if you want to get into nuclear engineering, the rate of fission is lower, but the efficiency of fission is high. And you start to have these additional neutrons that allows you to burn through some of the other stuff that you really is sort of mid-lived, right? So that's the stuff that you really need to kind of manage. but you're able to do that if you had a fast spectrum reactor. I'm going to show you some slides in a few minutes here that will speak to this, why some of the new reactor designs specifically are using this opportunity. I'll do a few more. Where do you expect the first SMR to start operating? I'm going to show that to you right now. Why does the Haley administration want to repeal the voter referendum on no nuclear in MA? Why not put on the referendum no voters? One thing I try to be a good communicator. I definitely am an educator and a researcher. I even dabbled into economics, but I do not understand politics. So I don't know where the referendum and what the decision is. So it's probably the one that I'm not qualified to answer. When do you expect the first SMR to start operating in North America? The earliest I've heard is the OPG 300. Yep, so there's a few in the hopper right now. In my honest opinion, I think there's going to be about at least 3 of these SMRs that would be operating between 2027 and 2030. Like all things new, I would give them grace. If they have a 3-year horizon, I would give them a sort of a 10 to 20% margin just because it's the first of the kind. Honestly, I think even in the gigawatt reactors, what we've shown now and documented, from the first of the kind to the second wave to the nth of the kind, there is a significant drop. And that is a lot to do with engineering and construction. Really, honestly, very little to do with the reactor itself. The reactor core is a small fraction of the total nuclear island. So there's a lot of different pieces that come together. So, we've got a perfected engine, but it needs to kind of do all the rest of the stuff to kind of work properly, right? So there will be some learning curves. I do anticipate that there will be a reduction in time as you go from that first of the kind to the second wave of maybe multiple, and then you will see that nth of the kind will reduce sort of. But I expect that there will be 3. Honestly, if 3 demonstration reactors don't come to completion and operate, we might as well write off nuclear. I mean, honestly, there's a time when one has to accept, right? I mean, I could take my son and teach him how to fish and give him all the opportunities I can, but maybe it's not his aptitude. Maybe hunting is his thing. So there may be, nuclear may be one of those industries that really cannot step up and do what they need to. But I do think we owe it to ourselves to give this generation an opportunity. They have new designs. These are not the designs of the past. They're the designs that are informed from our past experience of not only building and operating these reactors that have reliably produced power for us for 20 years. They are systematically addressing concerns around safety, spent fuel management, construction, cost, and reliability. So we do, as a society, hold them responsible, but we do need to give them an opportunity to show that they can do it. Given the political takeover of the decision-making in NIH, EPA, and other federal regulatory agencies, how can we trust the NRC decision-making? Meeting safety requirements at new nuclear plants, the NRC was not at all trustworthy during final permitting at Seabrook. I've read many reports related to NRC and Seabrook. Again, I have a general understanding of what it means, but I am not the expert on concrete calcination, for example. I think at some point, we as a society have to wonder, right? I mean, there is a concern with FDA. There is a question about vaccines. Everything that we do that could be grounded in science still can have an alternative scientific question that may seem unanswered. So I think it's a valid concern. I mean, who am I to argue? I'm not an expert. I make a choice for my kids that I want them vaccinated. I can give you reputable people who have published papers on the concerns associated with vaccines. So I'm not going to argue that NRC is perfect. But I think any federal agency that is responsible for regulating, responsible for setting standards, and is held in our world of transparency to the extent that we can, and providing the reports that we can read, at some point you have to accept whether you're just going to be on one side of the aisle or the other. But I think, we, at least for decades and centuries of our existence in the United States, we've trusted our governmental organizations. We trust our approach to transparency and responsibility. And we have experienced that not everything works perfectly. We have history with EPA, we have history with FDA, so I would say we have to continue to adapt and evolve, but we can't say that we cannot trust it. I would like to trust my federal agencies that are supported by scientific evidence and with competent people. But it's a choice at some point. How long do dry storage casks last, and how difficult is it to move to new containment vessels? So dry cask storage, actually, there was in Fukushima accident, there was a bunch of above ground dry cask storage that survived some of the tsunami brunt as well. These things are designed, to my knowledge, a minimum of 100 years of life, and at that point, they're actually monitored continuously. There's a bunch of different sensing systems in there that gives them the ability to sort of observe what the spent fuel looks like and where it is. And then at that point, you can move it into another dry cask, or you could have an interim storage. So there are some guidelines in terms of where you go and how you responsible. And as we all know, and I'm sure you are studied up on this, NRC requires anybody who has operated reactors and have the reactor spent fuel, that they still have to maintain that license and are responsible for that spent fuel. And we have trust funds associated with the responsible handling of spent fuel. So I can't speak for every country in the world, but I know that the U.S. by far is way in, I think, to the best of our ability to have a cradle-to-grave responsibility. And now we actually are seeing that the trust funds for each of the nuclear units are working. In fact, they're working so well that Americans are really good at doing things well, and they are amazing. We are the best in the world because we know how to self-critique ourselves, improve from our mistakes, and get better. I think that is kind of ingrained in our way of thinking. And so even the decommissioning work, we continue to get better. In fact, it is becoming much more efficient, reliable, where we are doing it at cost, and we have the money set aside, so we can't really ignore it.
I see a hand up here from Tina.
Okay, I was just going through the things, but yeah, Tina, you want to ask a question?
Tina?
Hear me?
Yeah.
Oh, great. Thank you so much for your presentation. There's so much information, really well delivered. If I was buying a nuclear reactor, I would buy one because you're a great salesman. I have a more on the ground question about your involvement at UMass Lowell in sustainability and clean energy climate plans. What's going on that you're involved in, and is
well, thank you for your comment. For a scientist
clear
to be
SMR at UMass Lowell to power up that school?
Okay, so yeah, thank you for that question. So thank you for your comment. I'm humbled that you think I'm a good salesman. I hope I am a better scientist and an engineer. I don't have a reactor to sell, but I do believe in everything I said, that we are coming up for a demand for energy. And I believe that this technology may have a part solution. I honestly don't think the nuclear, even if we could, we should power everything at 100% for nuclear, whether it's even fusion. So, but I think we should keep it in the mix and potentially look at about 30% deployment of the total energy demand. So just as a side. We, as a state institution with a existing research reactor that we've been operating for 50 years, safely, we have an operating staff, we have an understanding of how licensing works. We are talking, could we be somebody that we should, at least help furthering the technology, and how are we going to get that clean energy solution that is carbon neutral. So as part of, I'm part of the RIST Institute for Sustainability and Clean Energy. I obviously bring my nuclear engineering expertise, and to be very frank, we have some people who are genuine doubters of nuclear. In fact, we have a colleague who was a young child in Chernobyl at the time when she was growing up, and so I welcome the colleagues, very intrusive questions, and sometimes I say, hey, listen, I want to go back and read up on this and talk about it. So, but anyway, I think there is a lot that still needs to be unpacked. I think we are at a seminal moment in this country in terms of, self-reliance, the decoupling from the carbon economy, and we need to kind of find some things. So I kind of got through a lot of the comments and questions. What I want to do is, again, share a few things that might, sort of help conclude what I wanted to come here and show you, and then I'll go back to the questions if that's okay. So there are a few things that I kind of, just to sort of reset us to where we were, right? So why do I believe that there are some good telling signs that we could be going in the right direction? And so I talked about the decades of experience that we're bringing to this, so decades of operating reactors, right? And there's a noted independent review that we can get better at it. We also now have, yes, very costly and time delayed, but some experience of building gigawatt reactors. But the one thing that is actually happening really right now in real time and will happen literally within 12 months. So this is going to be a good indicator of how we can get this done, is restarting reactors. Restarting reactors is very difficult. It's the exact same thing. Again, we'll use the car analogy. If you just went away to Florida and then came back 10 years later and you think that you're just going to start that car and just start going, it's not going to be that way, right? I mean, my snowblower, right? Everybody, you got to clean the pipes, you got to clean the fuel, you got to make sure everything's working before you decide you're going to use it the next day or when there's snow on ground. So really, restarting is a very, very significant engineering demonstration of being able to take a reactor that was in some state of shutdown, right? So, and there's a few of these projects currently ongoing with actual investments with some specific timelines. And I think these are very clear indicators of where the industry is going to go. And this will give you more confidence in a 12 months period as to how our workforce is ready, how our NRC regulations are in place, and where we are trending. So this, again, is a very clear indicator of where we're going. So Palisade, which is actually an Entergy Holtec plant, they are currently the recipient of the Civil Nuclear Credit. This is a DOE's investment into the program. Holtec is actually putting its own money into this plant that Entergy decided they were going to shut down, right? So it was this same kind of plant that we had here in Pilgrim. And it was shut down in 2022. So fortunately, it was right at that timeline where they could kind of go back and look at it again. And it's a little bit higher, it's about that 805 megawatt electric power. They are looking to get this thing restarted by the end of this year or early next year. I think this will be a very clear indicator whether you have learned how to throw the line in the water and actually reel fishing. So this was a more near-term observation. 3 Mile Island Unit 1 is another one. This was shut down in 2019. Microsoft basically made an agreement and they put in $1.2 billion to restart this facility. Again, they want that up and running by next year. They feel that they're going to hit that target. This was done by Constellation. So again, there's also multiple players. So now that gives you confidence. There's a bunch of different people who are staging up competency, building up the workforce, bringing the ability to do these things. So Diablo Canyon, California is one of the second most toughest environments for nuclear power plants, and they really have a luxury of renewables at a bit of scale deployment, right? So we have about 10%, maybe 14% at best. At times in California, they can get up to 50% renewable on their Yeah, great. So they're very, very, fortunate in terms of how much sunlight and wind they have, in hydro. And even and so it's another sort of nuclear, skeptic, market. But there are two plants there that are now, ongoing for extension. So Diablo Canyon and, San Onofre. So again, these are some very telling signs that there's not just, people who drank the nuclear Kool-Aid, but people who are willing to put actual money, financiers, people who are in need of technology solutions today, the tech companies, communities that are looking to decarbonize, environmental groups. People are stepping up and revisiting nuclear in a perspective. And I think that this is a very clear indicator that there's something happening here that's not just a hoax. And then I want to kind of share, I think, some of the questions and maybe hopefully some answers here. So here are some of the technologies that are in various stages of the licensing. So NewScale essentially completed their license. And one of the things that they realized, their license that they had in January 23 in the failed project was licensed for a 50 megawatt electric plant. They actually made adjustments and now are able to squeeze in under 27 megawatts of electrical power by just some direct conversion amendments. And so they're actually now, each of their units is 77 megawatt electric. And that makes a big difference, right? So this is a significant percentage that you're getting more out of the same construction footprint. So there was a big announcement by TVA and an independent sort of a capital investment firm called Electra One for $6 billion of investment in deployment of these NewScale. So this just happened a couple of weeks ago. You can look it up. So yes, there was UAMPS was a project that failed. But failure does not mean it's bad. Failure means that something was not right about it. Maybe the financial agreements were not right. I would rather have a project fail early, because then whoever made the mistakes and had to change the things that needed to change, they can change. I would rather not have a plant that is 95% built and never fueled, because that's waste of everybody's time and money. So honestly, I think UAMPS is a good way for NewScale to improve their business model and provide better solution. Westinghouse AP300, again, it's a scaled version. So Westinghouse has an AP600, AP1000, and they actually have a small modular AP300. And that reactor is in a pre-application phase. The design attributes of this reactor is very similar because it basically has very similar design scaled of an AP1000, which means that their cycle to completion is going to be faster. They actually have a signed agreement in UK, and they're looking at the first of the kind commercial reactor build there. BWXT is another one of those developers. They are actually have a small modular reactor with M-Power that is in the NRC design certification process. And they also have a microreactor under what is called a Project Pele with the Department of Defense that is under the Idaho National Lab Dome demonstration project, and they're moving along in actual scaled engineering components demonstration. So this is not a paper reactor anymore. Same thing with GE Hitachi. They actually are the ones that I think somebody in this thing put. They're actually building their first reactor in Canada with Darlington and OPG, the Ontario Power Distribution, expected to get the first licensing review done by Canadians and potentially be the first reactor in North America to go to power, depending on how they get there. There's also a new player called Lost Energy. They essentially kind of said, well, look, we're going to take a light water reactor design. We're going to add all of this, the Generation 3 plus safety features, but now we're going to shrink it down in size to about 20 megawatt electric and bring to scale. They have a couple of power purchase agreement projects in the United Kingdom and are in conversations in Poland, where we're building, actually US is building few AP1000s. They're looking to leverage the experience there so they can actually build the PWR20 as they call their design. And then Holtec is actually now also in conversation with Palisade in Michigan to not only restart, but then they would have the engineering experience to add to their first of the kind Holtec SMR 300 design. So these are not hypotheticals. These are actual licenses in various stages of pre-application. And you can follow these along with NRC. They have to show where they are on various stages of licensing. So again, when you go to NRC's pre-application, yes, you may be kind of have a reactor design with some experimental validation, but when you're in the final stages of certification and approval, you really have to have everything demonstrated up. So this is no longer paper stage. And then there's the sort of these really exciting advanced reactors. Nanonuclear is one of them. Again, I could give a lecture on each one of these technologies in gory details, but this thing that you would notice is the second column. So these reactors, if you look at the, these reactors, all of them are essentially still using light water as a coolant. They're all using a different fuel. It's called LEU+, which means they go up to 5%. That actually has better spent fuel attribution and a longer fuel burnup, so you can operate for a longer time. But none of these actually use light water. So these would essentially have a very different profile of the spent fuel. In fact, some of them that come below the top six would actually use the spent fuel to burn in the reactor to produce electrical power. You're able to do that because you're changing the coolant, you're removing the moderator, and you're operating in the fast spectrum. It significantly shrinks your the size down, and you're able to do some things that you can't do with the light water. A lot of them use a very new fuel type. So the Triso fuel is by far it's like a little tennis ball. It actually has the containment inside of the tennis ball itself, so you really don't have the issues of the clad material meltdown and the barrier. Each of these Triso fuel particles holds the fission products in itself. Triso fuel is nothing new. It has been researched and lots of experimental demonstration and factory production for about 20, 30 years. But what's important here is, Nano is actually going through a joint review with NRC and the Canadian Regulatory Commission. The X Energy actually has a Hermes CP with a December, they have a shovel in the ground, and have another one they started construction in May 2025. And I was actually, the Kairos is in, X Energy is both in Texas and in Tennessee. Kairos likewise is actually secured a construction permit and are, in the construction phase in Oak Ridge, Tennessee. So I had the opportunity to see where they're going, and it's being sited at the retired coal power plant. And then lastly, Oklo, they have a couple of different designs. One of them is at the ARDP program, which is the Advanced Reactor Demonstration Project in Idaho National Lab. DOE has a lot of land there. They're actually building scaled reactors to demonstrate. So again, I didn't believe any of these guys 20 years ago. These guys actually have shovel in the ground. They have actual units that operate. And I have seen many of these reactors that we built back in the 50s and 60s at Idaho National Lab. If any of you have ever been to Idaho, they have full-scale reactors built back in the 50s and 60s that operated. They're doing the exact same thing now, some of them. Some of them are actually got construction permit in various different states, from Wyoming to Tennessee to Texas to North Carolina to Georgia. So this is no longer just a pipe dream. Can they do it at scale? Can they do it on time? Can they actually bring it to fusion? I think we will all be able to see that in the next 5 years.
I'm going to do a time check now. We're just about at 5:30. I don't,
So those were my last
I'm
slides.
sure we could, okay, we can stay
So I
on
have
for another few minutes. Yep.
I just have these that actually give a little bit of a blowout view for people who may be interested when I share these slides. But they're essentially condensed in that one deck. So last plug for me is if you're interested in looking at an actual operating reactor, I welcome you to UMass Lowell. We have an operating reactor. We have students who run them. They're all licensed NRC operators. And it is something, if you've never seen, seeing is believing. I strongly encourage you to come to the, a state, at our state university, and we would be very happy to show you the reactor. It is an engineering marvel that was designed before I was born, and it started operating just when I was born. So we have some really talented people, and we continue to have talented people. They're looking for new challenges, and I think we give them an opportunity. So with that, I will stop and I will take some more questions, and then we can wrap it up in comments. Maybe Ernie, I can ask you to tell me which questions you want me to try to address in minutes, because there's like 15 comments.
Yeah. I'd leave it to your judgment to.
I know. Let's see here. China is producing energy from solar that is decentralized, immediately available and cheap, and no dangerous waste. Absolutely. I have 46 solar panels on my roof. I have two Tesla, power walls. I am 100% committed to solar. But no matter who builds it in the New England region, we're not going to be able to do it. And even if I were to build it all the way in the Midwest, we would have to do significant capital investment of transmission, storage, and distribution. So I am all for it. But I think we cannot just wait for it to happen. So I'm not against it. I think it will be a great idea. Harm reduction viewpoint asked, how many people went sick and then died from nuclear waste compared to those from fossil production products? I am not an expert on it. I have worked in a nuclear power plant with radiation sources in an operating reactor for now almost 30 years. I have two healthy children who are not exceptionally smart in any way or have any superpower that I know of, except for annoying me. So I can speak to how I am a fairly healthy guy. I don't take any medicines, and I have two young men, and I have been around nuclear sources, actually more nuclear sources than what you would typically see inside a power reactor. And I don't have a third eye, so I can speak from that perspective, but I don't know. I mean, there's a lot of research there. What I could say is I'm a living example, and we have a bunch more. All of the people who work in the reactor, it's not hypothetical, right? We have operated 100 plus reactors for almost 50 years. And so we have hundreds of thousands of people who have worked at these plants. I think it would be an amazing thing if we could hide them all somehow. So I'd say, are there potential things that could happen? It's an industrial hazard, potentially could. Does it have the potential of destroying mankind? I think we've seen that it is. I believe that it does. The cost of nuclear is estimated to be higher than solar, wind plus storage. Nuclear is innovating, but also are batteries and grid storage, battery innovation faster. Maybe we don't need nuclear. I don't disagree. But, I think when you are talking about long-term planning should not be dependent on one technology, because you end up with a single point failure. So in my opinion, in engineering solutions, you must have alternatives where you sort of are hedging some of your opportunities so that you do not end up with a situation where a single technology failure. So for instance, Boeing has been making Boeing airplanes that we all fly in. Imagine an airline, JetBlue, if they had all of their airplanes as Boeing 737 MAX. When that one incident happened, the entire fleet will be down. That's just basic engineering management, where you do not want to have a single point failure. So I do think we should invest heavily in the development of renewable energy storage. I think is an important solution. But storage also has various different things. We have several faculty here working on storage that doesn't rely on solid state batteries only. There are other ways to store, particularly like molten salt. In fact, it's demonstrated in the Mojave Desert. Molten salt is a great way to do thermal energy storage, which actually can be very fast on recovery and much better duty cycle. So yes, I truly believe that we should invest in all of these technologies because I think they actually enable other technologies. Molten salt research really was done for the large scale solar that actually is helping nuclear, some of those reactor designs. So I think the advanced technologies can help each other. My understanding is that renewables are incapable of providing power needed globally going forward unless we insist that India and China can do. I fail to insist my son doing something who is 100% dependent on me for his subsistence and getting anywhere around. I don't think that we can insist and wield that power to large economies who are in rapid development and think that we can just bend them to our will. I think we can influence them. I think we can provide solutions that are reliable and approachable. And so I think we can be at the table. But I think the days of us dictating what others do are numbered. So I don't think we have that level of influence of asking what others do. Large technology companies are one of the ones who are demanding more energy for AI, for their search engines. Why should the consumers pay? I agree, they shouldn't. But how are you going to, you can put policies in place, but are you going to ban AI search engines? I think there is a cost of a non-adoption. In fact, I was asking this. I was like, who in their right mind would want to come to the most expensive, cost of living, energy cost, and land to build data centers? And the answer was, well, you need them at the demand centers. And we are some of the world's best innovators. We have the most number of institutions of higher education. We pride ourselves in leading in policy, technology, and everything else in the world. If we deprive ourselves, it's like asking our kids to go out and do math with the abacus because we don't want to use the calculator. AI is here and it is going to be there. So the answer to the question is, are we going to embrace it or are we going to say we're not going to use it? I can give you the answer to that. We cannot compete, no matter how good a mathematician you are, when everybody else is using a supercomputer and you're doing it with an abacus. So I think we got to do it responsibly. We got to force them to take some difficult decisions, but it is here. It is going to be here. So we have to stop pretending that it's not going to happen. Trust fund Holtec is using Pilgrim decommissioning trust funds to sue the state. Again, this kind of gets into the I'm not a legal expert. The bottom line is the nuclear industry is required to set aside funding. That funding is available in the trust fund, and it is it is allowing as an industry to act responsibly to decommission things. I have no idea what the other things that there are in there. The data center would need on the order of 1 to 2 square miles of PV plus storage and grid. Exactly. I mean, listen, I think AI guys are not tied. In fact, if you look at a lot of the tech companies, they were heavily invested in renewable energy development, right? I mean, if you look at Elon Musk, I mean, obviously part of his, business is in providing photovoltaic, and they have substantial investment in renewable energy, but I think they're also still coming back and thinking they're going to need something to offset what they're looking at the projected needs. So again, I feel like there are some very telling signs on folks who have all of the detailed numbers that you and I don't have, and they're making some decisions that are telling to me. Radioactive waste is of course terrifying. However, the planet is burning. Not clear how the dangers from nuclear waste compare to that. So I think we have to put it in context of spent fuel in the United States. You know, I can't speak to I'm not the global expert on spent fuel disposal and the fringe effects of radiation. And again, I say fringe not in a dismissive way, but you know, the acute effects are something that most of us have an observable on. These chronic effects over long term are not something that, unless you're a subject matter expert, you have the understanding. I have several friends who worked with mRNA. They're the experts. You know, when I went and took my vaccine for COVID, I trusted them, and I looked at the data and said, hey, you know what? I'm willing to take this risk. So I think that all of the data is out there, and we have to make our decision how we do it. Is impressed with China's solar installation with the equivalent of 3 gigawatts. I think it's similar. I don't disagree. I think we should deploy as much solar and wind as we can. The Holtec has never run a nuclear power plant. Your slide shows a pre-application. Correct. So Holtec currently is mainly a decommissioning and a spent fuel storage company. One of the reasons they're actually in the business, or hoping to be in the business, of spent SMRs is they're actually one of the ones that have the best experience of building the small size containment structures, the spent fuel, the storage cask. In fact, they have the most experience on manufacturing those kinds of containers that reliably have worked, and they're like global suppliers of this. So I think that's why they're interested in this. They may actually just decide to, remain in that business and let somebody else who's developing reactor technology like Westinghouse do the other. Again, I'm not a business developer, but I know why Holtec is looking at it, because they actually have a supply chain. I think we need to be careful in comparing China's rapid expansion of solar. I'm going to cut the slides here and maybe use the last couple of minutes if people want to stick around and maybe answer a question if there is one that has not been discussed here. Something that could be.
Well, thank you for staying on. We have, I don't know if Professor Gara, if you want to, pick a time where we'll end. I'm sure we could continue the discussion into the evening. Do you want to, you say, in quarter to 6, and we'll wrap it up, or are you game for more folks to?
I was just going to respond to, I'm not sure where my profile says that I support repeal. So I do think, so I'm not sure what the reference is to, but I can tell you what my position is. In absence of an ability to at least discuss the potential for nuclear power plants, we put ourselves at a disadvantage in terms of our ability to engage. And again, I'm a firm believer that if you're not at the table discussing things with people, your questions will never get asked. Like the way that you're able to ask me the questions, I can, if I don't show up because I'm afraid that you might ask me the questions that I don't like, then we never have a dialogue. So I like the title of your meetings. Deep dialogue is essential. And when we have a moratorium, it does not allow for many companies to even consider us as a viable discussion point. So from that perspective, I feel like repealing or removing that barrier allows us to engage with companies. But I don't know exactly the profile. So that's just my personal view. Something helpful for us to engage people. Hand up, Ed.
Yep. This has been a great discussion, and I really appreciate how open you are to answering all these questions. So again, I want to give you our thanks for being here. And as I mentioned at the start of your presentation, we do have a survey for our members and we're trying to get there views and impressions and address, what they feel are both the benefits and the issues associated with nuclear power. So I think you've really helped us sort of come to grips with some of those issues, and I'm sure this is going to be a continuing discussion here at Elders Climate Action. So again, I really appreciate your being here. You're taking the time and actually taking more time than we had scheduled for these presentations. So thank you very much. I really appreciate it.
Thank you very much for the invitation. And I don't have a tennis contract, so I can't play anymore. So, so I have more time on my hands.
Okay.
Thank you.
All right. Well, thanks very much. Thanks again. And thanks all who came to the presentation. And the video will be up on our website in the next day or two. And Professor Agara has told me he'll share the slides, so we'll put them up as well. And I'll be sending out an email to everyone who registered, can review what was said. And I know there were a number of people who registered who weren't able to come, and they'll be able to see the presentation as well. So thanks again, and we'll wrap it up. Thank you.
If you have a question, I can stick around for a minute if you want.
Okay.
Yeah, it seems to me that one of the big arguments against nuclear is competing with other sources of renewable clean energy. For example, which will be available sooner and which will be available in the scale that we need to do that. And I think there's both an economic and a risk argument there. And the question is, how do you evaluate those? For example, Bloomberg has now advertising 50 megawatt, 100 megawatt fuel cell modular installations for data centers. And they can put that in place in 3 months or 6 months, depending on how big a facility you want. Bill McKibben says, hey, we can do it all with solar. So how does one look at this from a policy standpoint to decide where we're going to put our bucks? As you say, we should do a little bit of everything. And you said that 30% of our energy can come from nuclear. But how do you keep track of that and measure that? What do you, as an academic, how do you evaluate that?
So, so I think if you start to look at it, and this is something that I've sort of I'm new to this, but I've been looking really last few years on economic analysis, right? And economic factors are influenced. So I actually have a model that we've developed, which is a technology model, economic model, a market model, which is essentially real-time pricing, and then I have a policy model. And what we do is we run so I'm a Monte Carlo guy. So Monte Carlo is a method in which you basically use probabilistic theory, right? So what is the probability of flipping a coin and getting a heads or tails, right? So with that kind of a modeling approach, we are looking at these 4 factors. When you start to evaluate them informed with real time, and then you can vary certain things. So what do I mean by that? So we can actually look at energy pricing and energy production as a function of time on a specific grid composition. And you start to add more renewables, you add more, solar and wind, right? But you can look at the market penetration and the feedback loop on how it will influence pricing, right? So we are kind of trying to figure out how to make that intelligent decision so that we are not depriving deployment of one technology at the expense of the other, right? And then the other thing in at least in US, there is always that capital investment that drives to some extent natural competition, right? So, if there was an unproven technology, and that's why I believe that some of these nuclear guys, if they can't deliver, they're going to be useless. I mean, the capital is going to dry away, right? I mean, the governmental's policies and subsidies can only get you so far. So I feel that there is room, a measured approach to success, right? So I looked at solar 10 years ago when I bought my home. At the time, the technology was not there to give me the production that I thought I needed. And I didn't have the utilization, and this other technologies were not there. So capacitors, I don't know, some of you may have solar panels. So like you need that interconnect to the grid. So there are lots of things that I actually evaluated at the time, and I continued to evaluate as they were improving until the time when I saw, so I have two curves, and then the technology maturation. And so when that came to an intersection point with the best federal and state initiatives, I came up with my conclusion as to why now is the time for me to deploy my solar panels, right? So I think that I mean, and I'm just a single homeowner with making a decision on $30,000. So when somebody's writing a 1.5 billion or $5 billion commitments on their business's bread and butter, I imagine they have fairly rigorous models, and they're looking at the technology maturation and what level of investment they're going to do, and then look at where their benchmarks are before they go forward. It is no shocking surprise that all of these technology companies, Amazon, Meta, Google, Microsoft, they didn't just wake up one day and start investing billions of dollars in nuclear. They were looking at this stuff for more than 20 years. And so I believe that they're hedging their bets to say, where do we go? Amazon has never made a losing bet in the last 20 years, including USPS, FedEx, and they are currently invested in 4 different projects, including a development of the nuclear technology, right? In addition to all the renewables, which is why I think they are doing an all of the above investment, but they're doing measured investments in particular segments of geographical impact. So anyway.
I mean, maybe one of the solutions is to look at it regionally. Clearly, New England is against nuclear, but you go ahead and you take geographic areas and you apply one technology there and another one elsewhere. So
Yep.
it gives you the diversity you need that you've been advocating for, which I think is the right way to go. But thank you very much. This has been very helpful. Like the discussion, love the questions. Very appreciative.
Love the questions.
If I can, I can sort of throw in a comment here. I don't know how germane it is to your question, Ed, but Professor Gower, you referenced the recent ISO New England economic study, which if I haven't read it all in detail, but my understanding is that they are recommending that the most economical approach to meet our carbon targets for energy production would include SMRs, small modular reactors, in the 2040 timeframe. And as I understand it, that is because in their own modeling, they're showing that as the penetration of wind and solar gets higher and higher, and we don't have the ability to store excess generation over seasons, that the curtailment becomes a big issue. The amount of wind and solar and storage that would be required to get the marginal improvement in our decarbonized energy becomes so high that the need for dispatchable, firm, clean electricity, even if more expensive on a per kilowatt hour basis, becomes economically viable at that time, which according, if I understand it right, to their analysis, is in the 2040 timeframe. Is that your understanding as well?
Yeah, I do have a. I'm sorry. Go ahead.
Go ahead. No, go ahead.
You go ahead, Jitesh.
Oh, I was just going to say, it's basically so there's actually even storage technologies that are in the low TRL, right? So there's actually something called flow batteries. We have a few faculty members who work. So these give you that not the hourly or weekly offsets on storage, but now you can get, you can stretch that time, right? But the TRL levels are low, which means you're really going to need a few more decades to get those kinds of energy storage solutions in play. So yes, that's why they're looking at, and it's a conservative view on saying, okay, well, we're not going to be in the mix on the first of the kind, right? So I think a lot of those are already in play for the SMRs. Our populace may also sort of be tentative on adopting the second wave. So that's, if things go, that will be in the 2035 in terms of order books. So that's why the 2040 timeline, right? So that gives us, that stretch. But if something goes faster, there could be some microgrid solutions. So the ISO does not actually capture that. So what do I mean by that? If the microreactor technology scale works, now you've got these pockets of 10, 20 megawatt electric power systems that could potentially, for like a university, may be able to, take that demand off the grid, right? So that is another thing that will sort of alleviate some of your demand curves. And so those are microgrid solutions that don't factor into this large grid solution where SMR deployment is.
Of course, another factor that's driving up the pricing is that as long as you have every supplier to ISO New England, that ISO New England brokers get the highest price of the last bit of energy that came on the system, no one has an incentive to reduce that peak because the lowest cost producer gets paid for at the highest cost producer's rate. So that to me is a broken system. There's got to be some way to reduce the incentive to have that fast acting turbine at $1,000 a megawatt hour not be built. But every solar producer around the state that's producing energy at that same time is going to get that $1,000 per megawatt hour, which is crazy. That's an argument for having storage. It's an argument for having storage because storage is somewhere between the $1,000 a megawatt hour and the $17 a megawatt hour that you pay. But that pricing system just doesn't create the incentive to continue to develop massive low-cost storage. So just an editorial comment.
Yeah, sounds like an experience that I need to tap into. Maybe yeah, that what you described is some of the factors that we may not have looked at very close. I mean, would love to add into our modeling curve. I appreciate very much the dialogue, and I've learned a lot from this engagement. So thank you for the opportunity. And now I should jump off before my wife calls me with the two boys. I got a 40-minute commute back home. So thank you again.
Thank you.